Next lesson of Chapter 8, 8.6 is titled Radical Expressions and Rational Exponents. We're going to kind of go away from the rational functions that we've been dealing with and rational expressions that we've been dealing with in this chapter and just kind of change gears into something different. We'll be kind of similar as we'll be dealing with rational exponents. So exponents that are fractions, so I guess that kind of fits in this particular chapter a little bit, but it'll feel a lot different than what we've been doing. First, what I thought we would do is review a little bit on how to simplify radicals. Much of this hasn't been done since the first chapter of the course, so it's been many months since we have. So when I've got just a square root, okay, what I do is use product property of square roots. I break down the 75 into a product. One of those numbers must be a perfect square. Okay, I take the square root of 25. Square root of 25 is 5. And then we can multiply these together and we get 15 square root of 3. The next example is one where we're dividing by a square root, and we have to simplify this by rationalizing the denominator. So we multiply top and bottom by square root of 3. So we get 4 square root of 3 divided by the square root of 9, which is 4 square root of 3 divided by 3. The last one is one that's a little different. I don't recall that we really saw in the first chapter how to do a square root that had exponents underneath it. So let's talk about that. I'll show you maybe one way to do it, maybe a different way to do it later, but maybe just to ease into it, I'll show you maybe a simpler way to see it, or a more easy to understand way to see it. How about that? Like a big square root here. The 8 is 4 times 2. The x to the third is x squared times x. The z to the 8th is z squared. We need one more, like that. So any perfect square comes out. All these z's, they all get to come out because they're all perfect squares. Okay, so the perfect square is on the outside. The 4 becomes 2. X squared becomes x. This z squared becomes z. And then I have another z, another z, another z. Under the square root, what's left over is the 2, an x, and a y. If I put these z's together, we have 2x z to the 4th square root of 2xy. Okay, so there's one way to see a problem like this. I'll show you another way to see that kind of later on in the notes when we get to see another example like this problem. Alright, next I just wanted to show a list of perfect squares. Perfect squares that it is helpful to know these. You know, this is Algebra 2 and we're all kind of sophomore, junior age. We should definitely have a list of perfect squares memorized that just kind of come to you real quick. It's going to make life in this section dealing with square roots much, much easier. Now, when simplifying radicals that have higher indexes than square root, so for instance cube root, fourth root, fifth root, sixth root, it's helpful to know some higher powers of numbers. So here's just a list in your notes of perfect cubes 2 through 9. It's just good to have memorized. Okay, a list of some fourth powered numbers, and then I just put a list in here of like powers of 2. You know, the ones that kind of show up the most often that you'd probably be beneficial to know. So simplifying some radicals that are not square roots. Here we go. I've got a cube root. I'm going to use the same property of radicals for all of these that I do with square roots, and that is I want two numbers that multiply to 56. Okay. One of them though has to be a perfect cube. Okay, we have to have that happen. So I know, for instance, that 2 cubed is 8, and 8 divides 56. 8 times 7 makes 56. The 8 is a perfect cube. it comes out of the cube root. Cube root of 8 is 2. 2 cube root of 7. Same exact principle that we would use if it was a square root. We're just using a cube, not a square. 54. I need two numbers that multiply to 54. Well, let's see, I know that 3 cubed is 27, and 27 divides 54 2 times. So 27 comes out as a 3. Got the 2 left behind. And finally, 162 under a fourth root. Well, I know that 3 to the fourth power is 81, and 81 divides 162. 81 times 2 is 162. 81 is the fourth power. It comes out as 3. Fourth root of 2 left over. So same exact principle as square roots. We're just using perfect cubes if they're cube roots. We're using fourth powers if they're fourth roots. Okay, how about simplifying radicals that have variables underneath them? Maybe I'll show you this first one two ways, and then you can decide which one is easier. I'll show you first how I did the example before that had a square root with variables, and you can see if you like that. So cube root of 27. So here's kind of technique number 1. 27 already is a perfect cube, so I'm not going to break it down at all. X to the 7th is x to the 3rd times x to the 3rd times x. Perfect cubes all come out. So 3 comes out, x comes out, x comes out. Cube root of x left over is 3x squared cube root of x. There's one way to do it. The other way to do it, which I'll show, is, well, first of all, the 27, it comes out the same. And then here's kind of how I cheated or speeded up. I just simply take the 3 and divide into the 7. Okay. How many times does 3 go into 7? The answer is 2. So I take 2 x's out. How many x's were left over? In other words, what's the remainder? The remainder of x's is 1. Notice this answer is exactly the same, but maybe got out a little bit faster. So let's maybe do the next one that way. So I have fourth root. 32 is 16 times 2. 16 is a fourth power. It's a fourth power of 2. So 16 comes out as 2. And now divide these. 4 goes into 4 one time. 4 goes into 6 one time. And left back underneath the radical is this 2. And the remainder that came with that was left over with the y's. 4 went into 6 one time with 2 left over. Okay, last example, I'd begin by putting these together. Cube root of x to the 9th. Since they're both cube roots, we can just multiply these like we normally would. Okay. Then let's just divide this. 3 goes into 9 3 times with no remainder. So no radical part of this answer. Next, what about rationalizing the denominator with radical expressions that aren't square roots? Okay. We have 5 divided by cube root of 3. You're still going to multiply top and bottom by something, but it's not going to be the cube root of 3 this time. It's going to be the cube root of 3 squared. Here's what we're trying to do. This 3 over here is a 3 to the first power. Okay. I'm trying to work this out in such a way that the power here and the power here add to the index of the radical. Okay, so watch what that makes. In the numerator I have 5 cube root of 9. The denominator is the cube root of, this is 3 times 9, which is 27. That's a perfect cube. That's what I'm trying to make. Answer is 5 cube root of 9 divided by 3. The idea is to form a perfect cube in this instance so that the radical is not in the denominator of that fraction anymore. Okay, the next one I could begin by splitting it up. Cube root of x to the third over cube root 7, which makes just x divided by cube root 7. Now we'll multiply top and bottom by a cube root. This is 7 to the first, so we need 7 squared. Get x cube root of 7 squared, which is 49, over, this is just going to simplify to 7. Alright, 2 more to try. Same thing, same type of problem. This is the same as the 4th root of x to the 8th divided by the 4th root of 9. The numerator becomes just x squared because 4 goes into 8 twice. The denominator can be thought of as the 4th root of 3 squared. I'm going to reduce 9 a little bit if I can. Now this time I have to multiply top and bottom by a 4th root. And I already have 2 powers of 3. So the question is, how many more powers of 3 do I need? The answer is 2 more. Trying to get to a total of 4 powers of 3 because that'll match the radical. Numerator becomes x squared times the 4th root of 9. Denominator becomes just 3. Next one, I begin by splitting this up like I have been previously. So this is 4th root 16x to the 5th over 4th root 5. 16 is a perfect 4th power. It's 4th power of 2. X to the 5th, 4 goes into 5 one time with 1 left over. Okay, so to rationalize this, to bring this up, I'm going to multiply top and bottom by a 4th root. I've already got 5 to the first. I already have 1 power of 5. So the question is, how many more powers of 5 do I need? The answer is 3. So the numerator becomes 2x. Because these are both under 4th roots, we can combine them into 1 4th root. 125x divided by 5. Now let's look at rational exponents, fractional exponents. And the trick to this, the trick to being able to do this, is that fractional exponents are just radicals in disguise. If I see a raised to the 1 over n power, it's the same as the nth root of a. Okay, so as an example, if I gave you 16 to the 1/4, what that means is the 4th root of 16, which is 2. Okay, and similarly, a raised to the m over n is the nth root of a to the mth power. Okay. In both of these instances, notice it's the denominator of the fraction that is the radical index. Okay. Example, if I were to give you 27 to the 2/3, that means the cube root of 27 squared, which would be 3 squared, so we'd have 9. So now just some practice of kind of the two examples we just saw on the last slide. 64 to the 1/3 power can be rewritten as the cube root of 64. That's a perfect cube. It's just 4. 4 to the 5/2 is the square root of 4 to the 5th power. Square root of 4 is 2. 2 to the 5th power is 32. And 625 to the 3/4 power is the 4th root, 625 cubed. 4th root of 625 is 5. 5 cubed is 125. And how about simplifying some expressions using properties of exponents, like when you combine exponents, when do you add them, subtract them, things of that nature. Negative exponents like this one here. Well, the first one, since we are multiplying, the rule says you add the exponents. 3/8 and 1/8 is 4/8. Well, 4/8 reduces, so you're certainly allowed to do that, to 1/2. And then a 1/2 power, we now know that's really just a square root 36, which I didn't say it before, you don't have to put the little 2 there, it's a square root, of course. And that's just 6. Okay, the next one we've got a negative exponent. So I begin by making the negative exponent positive. We do that by turning this into a fraction. 1 over negative 8 to the positive 1/3 power. That's the same as 1 over cube root of negative 8, which is the same as 1 over negative 2, or negative half. Last one, when we are dividing, the rule says that you can subtract the exponents. So this would be 5 to the 9/4 minus 1/4 is 8/4. Reducing that fractional power makes 5 squared, which makes 25. On this last slide of section 8.6, you find two problems. You might want to pause the video here and try these two problems, and when you're done, resume and kind of check your work. First one is a multiplication problem, so we add the exponents. Add to 18/9, which reduces to 2. 7 squared gives us 49. Next one is a division problem, so we subtract. 3/4 minus 5/4 is 2/4, which reduces to a half, and that is the same as a square root of 16, and we get 4.